Hello everyone. In this video we're going to review the reactions from chapter 12, which talked about oxidation reduction reactions. And remember, more carbon-oxygen bonds meaning that something is being oxidized. More pi bond also indicates that something is being oxidized. Alright, so suppose you start from an alkyne. One of the reactions that we talked about is hydrogenation reaction, right? Where we're adding hydrogens across pi bond. And that particular reaction was catalyzed in the presence of a metal surface, right? You have hydrogen in the presence of a metal surface, which could be platinum, palladium, or nickel. And what it does, it completely reduces an alkyne into an alkane. And we have 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6 carbons. So it goes all the way into just a simple hexane, where it was 1, 2, 3, a 3-hexane. Okay? So what if we wanted to trap it at a transalkene or a cisalkene? What we saw is we could use two different reagents, right? We could use sodium metal in the presence of liquid ammonia, and then what we get is a transalkene, and that's because sodium was an electron source in this case. And again, we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and it is a transalkene, right? End up forming a transalkene. If you wanted to trap it at a cisalkene, what we do is use a different reagent. Right? It's very similar to halogenation in the presence of platinum, palladium, or nickel, but instead of using platinum, palladium, or nickel, what we use is what we call a poisoned catalyst. One example is nickel boron. Another example was Lindlar's catalyst. Right? And then what we get is a cisalkene. So we have the alkene, and the two groups attached to it are cis to one another or on the same side. But we had 1, 2, 3. So 1, 2, 3, 3. I'll just draw it this way. All right. So, and if we wanted to go from the transalkene or from the cisalkene to the alkane, we could definitely do so. And what we use is hydrogenation reaction in the presence of a metal catalyst. It could be platinum, it could be palladium, or it could be nickel. So I'm just going to use a different one, right? But either one. It could have been platinum, it could have been nickel, it could have been palladium, right? So actually, so not to confuse you, I'm going to keep them all as platinum, right? So you don't think nickel or palladium are only for one of those. All right, but the metal could be platinum, palladium, or nickel. So that was hydrogenation, right? But it's not only specific to an alkene, it can also reduce a keto group. So you could be, so here's an example actually. Here's a keto group, here is an alkene, and here is an alkyne. And if you go in and run a hydrogenation reaction in the presence of a metal catalyst, what you get, it will reduce everything within the molecule. The keto group will end up being an alcohol, the alkene will end up being an alkane, and the alkyne will also end up being an alkane. Okay, and then we talked about two more reducing agents that were more selective towards a keto group, right? So just going to make a double bond right here. One was known as sodium borotetrahydride. Let's actually erase this. All right, this video is not meant to go over the details. It's simply helping you predict the product, right? So one was sodium borotetrahydride, and that is typically run in a protic solvent. Methanol, ethanol, water, right? And just going to keep it water. But it's run in any protic solvent, and what it does, it's selective towards the carbonyl oxygen. It would reduce the carbonyl oxygen into an alcohol group. The pi bond remains in its place. It's still the oxygen, but it's basically adding a hydrogen to the oxygen and a hydrogen to that particular carbon, right? So you're adding two hydrogens across those carbon-oxygen bonds. Another reagent that forms the same product is lithium aluminum hydride. Lithium aluminum hydride, which is often abbreviated as LAH, lithium aluminum hydride. But because it's very reactive with water, instead of it just being run in water, we add water as a second step. And it is really the hydrogen from water, or the solvent in this case, that ends up protonating an alkoxide ion. And the hydride from the reagent ends up adding to that carbonyl oxygen. All right, so that's lithium aluminum hydride. So the hydride is acting as a nucleophile in this case, and the lithium aluminum hydride is more reactive than sodium borotetrahydride. So what we saw is if we start with an alkyl halide, for instance, and we go in, lithium aluminum hydride again is abbreviated as LAH. If we go in and add lithium aluminum hydride, it is a hydride source, right? So I'm actually going to go ahead. Okay, this is not supposed to be about mechanisms. So it's a hydride source. The hydride is going to attack this carbon. We have the loss of a leaving group, and then we end up forming an alkane. So we can go from an alkyl halide to an alkane in a single step, right? So it's actually a single step. This requires water because we form an alkoxide and the water protonates the alkoxide ion. And we also saw lithium aluminum hydride that can actually open up an epoxide. So if we have an epoxide, because this can act as a nucleophile, it's a hydrogen atom with 2 electrons that can act as a nucleophile. If we add lithium aluminum hydride in the very first step, that hydride will act as a nucleophile. It will add to one of the carbons. You're breaking a carbon-oxygen bond. You end up forming an alkoxide ion. So in the second step, it could be an alkyl halide, and you could extend it, or it could be simply water. And then water will come in and protonate that alkoxide ion that forms. All right, those mechanisms are a lot of fun to do, so you should be able to learn them. Meanwhile, I'm just helping you predict the product. All right, or very quickly reviewing predicting products. So those are some strong reducing agents, but lithium aluminum hydride is acting as a nucleophile, all right? And it's more reactive than sodium borotetrahydride. Sodium borotetrahydride is more selective towards only carbonyl oxygens, all right? But both are selective towards carbonyl oxygens. They do not react with pi bonds of an alkene or an alkyne. Okay, so now we're going to review some more reactions from chapter 12. But first of all, let's erase this. Okay, I'm going to keep this on. Okay, so now we're going to learn about, or we're going to predict dihydroxylation reactions where to an alkene or to a carbon-carbon double bond, you're adding 2 groups, right? And they're both hydroxide groups. So I'm going to draw a cyclohexene, right? So there are 3 different reactions that add 2 alcohol groups to a carbon-carbon double bond. So we start off with an alkene, and what we end up forming is 2 hydroxides, right? What we call a diol, right? 2 alcohol groups. So we can go from an alkene to a diol, all right? So if you were to name this, let's actually do that. So it's a cyclohexene. Cyclohexane, but it has an alcohol group. So what we do is we get rid of the E, right? And then it has 2 alcohol groups. So -1, 2 dash diol, all right? Or 1,2 cyclohexane diol. All right. You get rid of the E and then add di because it's 2 hydroxide and OL because it's the alcohol group. All right, meanwhile, those reactions do have stereospecificity as either an anti-addition or a syn addition. So we'll start with a syn addition, where both hydroxide group are being added to the same side of that carbon-carbon double bond. One reagent that can achieve that is potassium permanganate. But that particular reaction is typically carried out in the presence of sodium hydroxide and in the cold. And what we get is syn dihydroxylation, and that's because potassium permanganate, when the pi bond attacks one of the oxygens, both will bind to the same side or phase of that alkene. So we end up getting a syn addition, right? Another reagent that can form a syn dihydroxylation is really osmium tetroxide, right? But osmium tetroxide tends to be pretty expensive, so we end up adding a molecule that can re-oxidize it, all right? So we add NMO. All right, so that's, again, syn dihydroxylation. What if we wanted anti-dihydroxylation, where both groups are being added to trans to one another, where one is a wedge and one is a dash, what we refer to as an anti-addition, right? Recall halogenation, right? It goes through a brominium ion bridge where you end up, and then if you open up that brominium ion bridge, you end up getting an anti-addition. Recall ring opening of an epoxide. Those two groups end up being an anti-addition. Well, in dihydroxylation, what we end up using is a reagent that has a peroxy acid. And what a peroxy acid is R being a carbon chain, but that molecule has a carbonyl oxygen, an oxygen, and an alcohol group, right? That's an example of a peroxy acid. The simplest is, a peroxyacetic acid, where this is simply a methyl group, but it could really be any R group, right? And that very first step actually ends up forming an epoxide. So step 1 yields an epoxide, and step 2 is typically an acid, and the acid will protonate the epoxide, open up the epoxide, and then we get an anti-dihydroxylation. One well-known peroxy acid that is used is metachlorobenzoic peroxy acid, right? And so that particular reagent, the peroxy acid, could be MCPBA. So I'm just going to write MCPBA, right? MCPBA is an example of a peroxy acid. Okay, so we get an anti-addition. So now let us discuss a few more. We're going to discuss 2 more oxidizing agents, right? And this is an example of an oxidation, right? More oxygen, carbon-oxygen bonds. Okay, so we can oxidize an alcohol group. I'm actually going to erase this. Actually, yes, I will erase this. So if you wanted to form an epoxide, you could simply add MCPBA to a pi bond instead of doing halohydrogen formation and then adding a base. Okay, now, so now suppose we have a secondary alcohol. If we add chromic acid, and really anything with chromate, typically ends up as a very strong oxidizing agent, right? Oops. Where's the chromium, right? And the hint is the chromate. think with any reagent with a chromic acid is a very strong oxidizing agent. And what it will do, it will oxidize a secondary alcohol into a ketone. Okay. If what you had instead is a primary alcohol, it is a strong enough reagent that it will oxidize that primary alcohol into an aldehyde, and then it will oxidize that aldehyde all the way into a carboxylic acid group. So it is a very strong oxidizing agent, right? So if you have a secondary alcohol, you end up forming a ketone. But if what you have is a primary alcohol group, right? So this is a primary alcohol group, and then you end up using any form of a chromic acid, then you end up forming a carboxylic acid group, right? Very strong oxidizing agent. What if you wanted to trap it right at the aldehyde and you start off from a primary alcohol and you want to stop at the aldehyde rather than forming a carboxylic acid group? Then we could use a less reactive reagent, right? So if we have a primary alcohol and instead we end up using PCC, which is typically carried out in methyl or dichloromethane, then it traps it right at the aldehyde. If we use that same reagent for a secondary alcohol, it will stop it at the ketone, right? It'll oxidize it, but you can only oxidize a secondary alcohol once, right? Okay, what if you have a tertiary alcohol? Perfect, you can't really oxidize a tertiary alcohol because you can't really add a double bond, right? Perfect. So, strong oxidizing agent is anything with chromate. It'll oxidize it all the way, if it can, to a carboxylic acid, and the hint is that you're starting with a primary alcohol, it goes to a carboxylic acid group. If you have a secondary alcohol, it goes to a keto group, right? If you want to trap it at the aldehyde, you would have to use PCC in methyl dichloride. All right, so there is one more reaction that I forgot about, and that is oxidative cleavage, right? So if you start with a carbon-carbon triple bond, and I'm just going to make it asymmetrical, and you go in two steps. It's oxidative cleavage, or known as ozonolases. For an alkyne, our second step is water, and what we're doing is we're breaking up that carbon-carbon triple bond. So I'm just gonna dot those two carbons. So we end up getting, here's that particular carbon, and then 1, 2, 3. All right, so it oxidatively cleaves that alkyne, and what forms is a carboxylic acid group. Right? And you get both products. However, if you start from an alkene instead, and I'm just going to make it into a cyclic molecule. Sorry, I'm going to erase this very quickly. All right, and here is a pi bond. All right, it's going to cleave a carbon-carbon double bond, but instead of adding a carboxylic acid group, it simply adds a keto group, right? So it's like you're breaking this carbon-carbon bond. In that particular reaction, instead of being in water, it's in DMS, or we could use zinc chloride in water, all right? But it's typically in DMS. If the reagent is water in the second step, we know that we're starting from an alkyne. So you're basically cleaving that carbon-carbon bond, right? So again, I'm going to put a dot here and a dot here. So we know it's 6 carbons long, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. At that particular carbon, which was one of those two carbons, we had a methyl group. So here's that methyl group. And then at the second carbon from one end, we had a methyl group, right? And what we end up adding in that particular reaction is a carbonyl oxygen on either end of those two. So a carbonyl oxygen will add right here, and then a carbonyl oxygen will add at this end, right? So it can form either an aldehyde or a ketone depending on the alkene if it was substituted or not. All right, so those are all the reactions in chapter 12. Again, this is just a brief summary very quickly of being able to recognize the products, right? The details, we went over it in class for the most part. Okay, good luck on your exam this week.